Okay, so we would like to examine and analyze in detail an example of a Banach space. We will start with a finite-dimensional Banach space, and we will try to pretty much examine the three aspects that make a set equipped with the corresponding structures a Banach space, meaning the vector structure, the vector space structure, the norm on that vector space, and finally, the fact that it's complete. Actually, one might say that the third one is not a structure, but rather an attribute of the other two. So let's begin by defining our space. So we will start with Rn. We recall that Rn is simply, at least for the purposes of this context, the set of all n tuples of real numbers. So this is what we call an n tuple, meaning a collection of n numbers put one after the other. So here xi belongs to R for I equals 1, 2, and so on. So let's try to give everything in full detail. So we need to describe the two operations that make this set into a vector space. And I think this is quite straightforward. So if we have two n tuples, in order to add them up, what we do is we add up their coordinates, their corresponding coordinates. And sometimes we say that these are coordinate-wise operations. So this is the addition. And the scalar multiplication, so suppose that lambda is a real number and we want to scale the vector x1 up to xn by lambda. This will be lambda times x1, comma, lambda times xn. And now one would have to check that all 8 properties of a vector space are satisfied, but this is almost a nauseating triviality. I mean, for example, if you want to check the first property, then you would have to take 3 vectors. That would be the associativity. And you would like to check that this sum plus a third vector equals this. So the first vector plus the sum of the other two. Okay, so pretty much in order to check that, even though it can be done again coordinate-wise, I mean, what is the first sum? So the first sum is x1 plus y1 and so on, plus z1. So now, typically one would say, well, when you add up these two things, you find, for example, on the first coordinate, x1 plus y1 plus z1, and I could write it right away. However, let me again follow a completely, a possibly nauseating path by just telling you that this is the same thing as x1 plus y1 plus z1 all the way to xn plus yn plus zn. I mean, nobody would ever write this for real numbers, right? I mean, remember that this is a real number right here, so you would drop the parentheses right away. But this thing is pretty much, you can carry out the parentheses to the last two summands on each coordinate. So this will be x1 plus y1 plus z1, comma, xn plus yn plus zn. And here, this is by definition x1, comma, xn plus y1 plus z1 here, all the way to yn plus zn. And finally, this is equal to what we wanted it to be. You see, initially, I wanted to follow a different path. I just wanted to show that each side is actually equal to the vector that has coordinates xi plus yi plus zi. But this way, I equally like it, because this way it's shown in an explicit way that what we do is we actually take advantages of the properties of real numbers, in this case of associativity. And exactly because everything is happening coordinate-wise, all the properties are true because they're checked for each coordinate. So if you like, you can verify the other 7 properties, but I will stop here. I hope we all believe that this is, or we should believe that this is a vector space equipped with these 2 operations. And now let's proceed with the norm. So I'm going to define what is known as the 1 norm. And the 1 norm is nothing else but the sum of the absolute values of the coordinates. And when we take this to serve as a distance, so we can take it to serve as a distance by taking the norm of the difference between 2 vectors. It usually has a very interesting name. It's called the cab driver distance, because the idea is pretty simple. If you want to go from this point to that point, the usual Euclidean distance would have been this. But if you actually picture that you are on in a city with blocks, you would actually have to drive first this distance and then that distance, which is exactly what is going on here. And that's exactly how a cab driver would drive this, or, you know, any driver for that matter. Traditionally, it's called the cab driver distance, but we could just call it the driver distance between that is induced by this norm. In any case, let's check that this is a norm. So first of all, what do we need to check? Let's see. So the first thing that we need to check is that the norm of any vector is greater than or equal to 0. So is it? Well, the norm of a vector x1 plus xn is the sum of a bunch of non-negative numbers. So it has to be greater than or equal to 0, for sure. Okay? Because each number is non-negative. This is greater than or equal to 0, this is greater than or equal to 0. When you add non-negative numbers, you get a non-negative number. Second property, we would like to check that the only way that a vector has 0 norm is if it's the 0 vector. So does it follow that this is the 0 vector? And what is the 0 vector in this vector space? Obviously, the vector that has zeros on all coordinates. So why is this true? Well, if x1 comma all the way to xn is equal to 0, then that would mean that the sum of x1 plus x plus all the way, you see, I don't want to say x2, because if I start with x1 and I finish with xn, I even leave the possibility open that n is 1. Okay, when you say x2, pretty much you say that n has to be greater than or equal to 2, which is not a big problem because really we want to do higher dimensions here. But in any case, there's this funny little detail here. So if you have the sum of non-negative numbers being equal to 0, then all of them have to be 0. There's no other way this can be zero, which of course implies that x1 up to xn is simply the 0 vector. Okay, so we're good here. Let me write this the way I just advocated. And then we would like to show that the norm behaves nicely with respect to scalar multiplication. So if I take the norm of the scalar product of a real number by a vector, then this norm will simply be the norm of lambda x1 all the way to lambda xn. And this is by definition of the norm lambda times x1 plus lambda times xn. And this is equal to, because of the properties of absolute value of lambda times absolute value of x1 plus all the way to absolute value of lambda times absolute value of xn, which is equal to absolute value of lambda times absolute value of x1 plus all the way to xn. And this is nothing else but the norm of x1 up to xn. So we're good here. And finally, for the triangle inequality, again, you will see that everything reduces to real numbers, which is true both for finite dimensions and infinite dimensions. The only difference is that for finite dimensions, the transition from real numbers to vectors is almost trivial. In the case of infinite dimensions, it can be tricky because we have convergence. So we'll see the details in a different example. But for the moment being, let me suppose that I have the norm of the sum of two vectors. And I would like to check that this is less than or equal to the sum of the norms. Oops, let me take the sum of these two vectors. Again, it might be a good idea if you forgot what the properties of a norm is to refresh your memory. So I have to take the norm of the sum and so that it's less than or equal to the sum of the norms. And this is going to give us this vector. Which has norm by definition. Actually, you see I had started writing this little index 1 for all the norms, and at some point I stopped doing it, which is not a good idea. So let me put again the number 1 here, everywhere that I had a norm. Okay, so I think I'm consistent now. And this is the sum of x1 plus y1 plus all the way to xn plus yn. And here's the crucial part. This is less than or equal to what? Think about it. The first term is less than or equal to x1 plus absolute value of x1 plus absolute value of y1. Why? Because this is true for real numbers. Okay, I mean, there are different ways of checking this for real numbers, even by taking the properties of absolute values that any number is between its absolute value and the opposite of the absolute value. But the bottom line is that once you believe that inequality for absolute values, then it's immediate to get it for the norm of that we just have defined, or what we claim that it's a norm. So now you just redistribute the sums and you get all the x's together, all the y's together, and this will give you the norm of x1 up to xn plus the norm of y1 plus yn. Again, it's the one norm. And that means that we have in our hands a norm linear space. So we're good with these properties. So now let's show that it's complete. So first of all, let's denote this by L1n. So L1n by definition is Rn with, actually, you know what, I want it the other way around. So you will find both in the literature, but I want L1, I want the parameter that shows how the norm is defined, and then the n that shows the dimension underneath. So this Rn equipped with the one norm. So by definition, we denote it by L1n. So we would like to show that it's complete, is complete. Okay, and here, again, as you're going to see, it's a very straightforward argument, which is based on the completeness of real numbers, so don't expect any fireworks. So let me actually write this as a claim, but this is quite typical, and it always works so easily for finite dimensional spaces. If the space is infinite dimensional, then it becomes a little more interesting. So let's prove this fact. So how do we prove it? Okay, so let's try to use a certain notation. So imagine that you have a sequence of such vectors, and now we have to be a little careful. So let's say that the sequence is U1, U2, and the general index, let me call it M, and so on. So let be a Cauchy sequence of vectors in L1n. Okay, so what does that mean? That means that that for any epsilon greater than 0, there exists n naught in n, such that if m comma l are greater than n naught, then um minus ul is less than epsilon. Now, basically the idea is pretty straightforward. Let's see what the idea is. So take the vector u sub I and write it in terms of its coordinates. After all, it belongs to Rn, right? So I'm going to write it like this. I'm going to write it as x1, comma I, x2, comma I. Again, I didn't use x2, so let me go all the way to xn, comma I. So in other words, I have double index. The first index is the coordinate of the vector, and the second index is the place in the sequence. So I should maybe make the commas that separate the coordinates a little more pronounced on the commas that separate the indices. Okay, so what I know is that U sub m minus U sub L, the one norm, is by definition x1, sorry, is what we call them. So x1 comma m minus x1 comma L all the way to xn comma m minus xn comma L. And now I know that this has the property that it's less than epsilon if m comma L is greater than n naught. So that means that for any I with I being between 1 and 10, meaning I'm singling out one coordinate, I have that xi comma m minus xi comma L is less than or equal to the norm of um minus ul. So whatever you can do in terms of proximity for the ums and the uls, you can do also for the xims and the xils, which means that this implies that xim, this sequence, is Cauchy. Okay, because for a given epsilon greater than 0, the same n naught that works for um will also work for xim. And this is pretty standard. You will find this in the theory of Banach spaces that have, or of norm spaces, if you like, that have similar definitions for their norm all the time. That if you have a sequence of a Cauchy sequence of vectors, then that translates to a Cauchy sequence of their coordinates. The other way around is true in finite dimensions because you have a finite sum, but it's not true in general. So exactly because this sequence now is a sequence of real numbers, since xi comma m, again, this sequence is with respect to m, is a sequence of real numbers, is not any sequence, it's a Cauchy sequence of real numbers, it converges, right? We know that the set of real numbers is complete. And let xi be the limit as m tends to infinity of xim. And let's define u to be the vector x1 up to xn. We claim that um tends to u, i.e., what does it mean for a sequence of vectors to tend to a vector? That the limit as m tends to infinity of u m minus u, the norm of the difference, as a usual sequence tends to 0. Okay? Yes, but what is this limit? I'm sorry, what is this norm? This norm will be by definition, again, I mean the one norm, I shouldn't forget to write that. This will be x 1m minus x1 plus all the way to x nm minus xn. Okay, that's precisely the definition of the norm. Yes, but this tends to 0. This tends to 0. Why do they tend to 0? Because that's how we define xi. Xi was the limit of this sequence, which means that this difference tends to 0. And you have finitely many terms, so you have finitely many sequences that tend to 0. So their sum tends to 0. In other words, we just found the limit for our Cauchy sequence, i.e., the Cauchy sequence converges. Hence, L1 n is complete. Hence, it's a Banach space. So, in fact, one shows something much, much, much more general, that take any finite dimensional vector space and consider any norm on that vector space, then it's automatically a Banach space, meaning it's automatically complete. So what we proved is not just some oddity. The moment we cross over to infinite dimensions, we will see that completeness is not to be taken for granted. But for finite dimensional vector spaces, it can be taken for granted. And for any concrete finite dimensional space, pretty much what we just did is a prototype for how you prove that it's complete. For general finite dimensional vector spaces, one needs a little trick. And basically one shows that any finite dimensional vector space is isomorphic to a standard finite dimensional vector space with some well-known norm, which is known to be complete, and completeness is preserved under isomorphisms, and that's what establishes that. Okay, if you don't know what an isomorphism is, basically what I just said might as well be in Greek, but the bottom line is that it's a general argument. The basis, of course, of this argument is what we just showed, plus a theoretical argument that it's not so hard to establish if one knows the correct steps. So this completes our account of our first Banach space, albeit a finite dimensional one. But that's it. Thanks for watching.